Greetings, class. We'll be talking about combinations. So here, we're going to suppose that we only want to count the number of ways to choose R out of n objects without regard to order. When we looked at permutations in the last lesson, we cared about order. Here we don't, and this makes a difference. This is equivalent to counting the number of different subsets of the n objects that contain exactly R objects, and you'll see when we do some examples. So for instance, how many subsets of the set 1, 2, 3 contain exactly 2 elements? And order is not important because subsets, we don't care about order in a subset. So I'll list them out. 3 subsets, 1, 2, 1, 3, and 2, 3. Each of these subsets contains exactly 2 elements, so 3 subsets in total. Definition: the number of subsets with R elements taken from a set with n elements is called the number of combinations of n things taken R at a time. Here's the notation. Actually, it's a notational fog because we have a couple choices. I can use that first symbol, looks like a giant parentheses, and it's called n choose R, or I can use CNR. They both read n choose R, or the combination of n things taken R at a time. So both of those are perfectly okay. These are also, believe it or not, called binomial coefficients. You have seen these when you were a little kid taking elementary school courses. So it turns out, see below, that CNR, the number of combinations of n things taken R at a time, turns out it equals n factorial over R factorial over n minus R factorial. Looks a little bit like the number of permutations, but there's an extra term there. So here's the difference between permutations and combinations. Combinations, like I've just said a few times, not concerned with order. So ABC equals BAC. I suppose I could write that in set notation so it would really be mathematically true. Permutations are concerned with order. In this case, ABC does not equal BAC. The number of permutations of n things taken R at a time is always at least as large as the number of combinations, and that's because permutations are concerned with order, combinations are not. In fact, choosing a permutation is exactly the same as first choosing a combination and then putting the elements in order. So in other words, n factorial over n minus R factorial, that's the number of permutations of n things taken R at a time, that equals the number of combinations times the number of ways to put those R elements in order. So n choose R times R factorial. Thus, n choose R, the number of combinations of n things taken in R at a time, is, solving the previous equation, n factorial over n minus R factorial over R factorial, which is what I promised on the previous slide. So, in particular, let's look at the following results. These should all kind of be intuitive. First of all, n choose R equals n minus R. N choose R equals n choose n minus R. Now, this actually makes a lot of intuitive sense because if I've got n kids and I choose R of them, that's the same as having n kids and not choosing n minus R. So those combinations are exactly the same. N choose 0 equals n choose n. That's a special case, but it also makes sense that it equals 1. How many ways can I choose nobody? Well, one way. I don't choose anybody. That's the same as how many ways can I choose everybody? One way. In addition, n choose 1, that's the number of ways I can choose exactly one person out of n. Well, that's going to equal n. And by the symmetry rule, that's equal to n choose n minus 1. So these are things that you should just know. You'll get used to it. Here's the binomial theorem. I'm sure you learned this in high school. So it's a famous result. Here it is. It's easy to show that x plus y to the nth power equals this slightly nasty looking summation from I equals 0 to n of, whoa, look at that, the binomial coefficient, the number of combinations, n choose I times x to the I times y to the n minus I. Go ahead, do a couple of these by yourself. X plus y to the third power, you'll see that that equals x cubed plus 3x squared y plus 3xy squared plus y cubed. You'll see this. I'm going to let you do that by yourself, but this is a true fact, this binomial theorem. And indeed, this is where Pascal's triangle comes from. Again, I'll let you explore that for yourself. Here's a corollary, a very surprising fact, and that is that the summation from I equals 0 to n of these binomial coefficients, n choose I, that summation equals 2 to the nth power. Now, where would you get something like that? It really looks like it's coming out of nowhere. You add those coefficients up from I equals 0 to n, and you get 2 to the nth power. Where is that coming from? Here's the proof. By the binomial theorem, 2 to the n equals 1 plus 1 to the n. I mean, that's obvious. And that equals, let's plug in x equals 1 and y equals 1 into the binomial theorem. And so you get summation from I equals 0 to n choose I. Instead of x to the I, we have 1 to the I. And instead of y to the n minus I, we have 1 to the n minus I. Now, I don't think I need to go any further, but 1 to the ith power times 1 to the n minus ith power equals 1. And we are done with the corollary. Very, very nice. I will take a 2-second break and tell you that I'll never forget this, because on some Star Trek episode where they're going around the planet, and Mr. Spock is very concerned that the energy output of that planet has increased by a factor of 1 to the 10th power. And I didn't understand why he was concerned about that. Well, who knows? So let's do an example. An NBA team has 12 players. So I want to know is, how many ways can the coach choose the starting 5? And in this case, order doesn't matter, because we're just going to have 5 bodies put onto the court. Doesn't matter the order in which they come out, right? So I just want 5 players from that team. Well, that's easy. 12 choose 5, which is 12 factorial over 5 factorial over 12 minus 5 factorial equals 792. Now, of course, in reality, the coach is going to be more likely to choose a specific set of those 5 players because they're better than the other 7. But whatever. As far as my question goes, he could choose 12 choose 5. But he has to decide who his favorite 5 are, I guess. Another example. Smith is one of the players on the team. How many of the 792 starting lineups include that guy? Well, Smith is guaranteed to be on the starting lineup, and so that means that we need to choose 4 people from the remaining 11. 11 choose 4. Isn't English great? And so that equals 330. Smith gets one of the 5 positions for free. There are now 4 left to be filled by the remaining 11. So that's so nice. Let's suppose we have 7 red shoes and 5 blues. I don't make these things up. Let's find the number of linear arrangements of these shoes. So here's one of them. Red, blue, red, blue, blue, etc. Red rum. So there are 12 reds and blues in that order with 7 reds and 5 blues. How many ways can we scramble these guys? In other words, how many ways can I put 7 reds into the 12 slots? That's what it amounts to. Well, you don't need to think too much. 12 choose 7. How many ways to put 5 blues into the 12 slots? By symmetry. 12 choose 7. Same answer. So wasn't that easy? Now we know permutations, combinations, addition rule, multiplication rule. We're going to start putting these all together in the next 5 lessons, which have more complicated uses of combinations and permutations. And I think I can guarantee that they're going to be pretty fun lessons. So looking forward to that. We'll see you soon.